Good morning. Myself, Sowjanya Lakshmi, I'm a research scholar in the Department of Computer Science and Engineering, Sir M. Vishweshwara Institute of Technology, Bangalore, India. Today, I'm going to present a paper on communication-induced checkpointing-based fault tolerance mechanism using deep learning in IoT applications. IoT is widespread technology in many industries where data is collected through sensors and it is processed with respect to various constraints and requirements. The decision at the edges are taken based on the pre-processed data. This decision go wrong and create damages in the systems if taken based on some faulty information. Software faults, especially transient faults, are the primary contributors to deficient decision making. There are many fault tolerance and recovery techniques. Amongst the checkpointing is the best fault recovery technique based on restart operation. The existing fault tolerance mechanisms suffer from checkpoint overheads as checkpoints are not placed at required locations, instead are placed either periodically at many or all nodes. In our research, we describe a novel communication-induced checkpointing based fault tolerance mechanism designed to efficiently recover from transient faults while minimizing useless and forced checkpoints. LSTM, that is long short-term memory-based deep learning algorithm, is used in our approach to predict fault occurrences and place checkpoints only at required nodes. This proposed method also in turn improves system reliability and performance. To verify our proposed CIC-FTM, we have used IoT-based agriculture environment. Figure 1 depicts a fog-enabled cloud infrastructure. The key nodes are sensors that collect unstructured data, then processors convert data into structured input for decision making, then fog computing facilitates faster local processing over cloud computing. In IoT systems, the data transactions are prone to transient software faults. Example, sequence number fault, checksum-based faults, null character, and out-of-range faults. These faults disrupt operations and cause system damages. Existing fault tolerance mechanisms focus on fault recovery but face checkpointing overhead and inefficiencies. Checkpointing saves crucial information temporarily, including code, data status register, contents, environment and condition, access count of the files, file pointer, and file-related details, ensuring consistent system state. The type of checkpoint mechanisms are uncoordinated checkpointing. It is inefficient due to inconsistent node, which leads to domino effect. Then coordinated checkpointing, this directs to periodic or sequential checkpointing, which leads to checkpointing and storage overheads and useless checkpoints. Then at last we have communication-induced checkpointing. This combines the aspects of both coordinated and uncoordinated checkpointing, but has forced checkpointing issues, which leads to useless checkpoints. Hence, the problem to address here is to design and implement a more efficient communication-induced checkpointing-based fault tolerance mechanism, which intelligently places the checkpoint at required faulty nodes and initiate the restart process for fault recovery from the checkpoints. The introduction section also provides a comprehensive survey of various FTMs in distributed systems and their applications to IoT environments. We'll start from Petru, Ellis et al. Propose a combination of error detection, equidistant checkpointing, and rollback recovery to handle faults, though the approach may lead to time overheads. Hilary et al. Focus on reducing redundant checkpoint through communication-based methods, but face complexity issues in dynamic environments. IJEECS et al. Present a local checkpointing technique to reduce overheads, but it struggles with the coordination complexities. Simon et al. Introduced delayed CIC to enhance fault tolerance, but also encounter challenges with useless checkpoints. Roberto Baldoni et al. Propose an indexed-based CIC algorithm that reduces overhead but faces scalability issues. Further, Leovai and Manivanandi develop a fully informed CIC protocol, which is also called FINE protocol, to minimize forced checkpoint but still deal with communication overhead and implementation complexities. Jinho and suggest combining CIC with message logging for better recovery, but this approach still suffers from overheads and dependency issues. Neha Malhotra and Manju Bala designed a CIC-FTM for IoT systems that minimizes useless checkpoints but relies heavily on specific parameters and may not scale well in dynamic networks. Parmeet Kaur Jaggi and Avdesh Kumar Singh propose adaptive checkpointing for mobile computing grids, which is flexible but depends on available resources and may become inefficient in large-scale systems. Finally, Tan et al. And Nurul Absar et al. Explore the use of LSTM network for fault detection, while Syed El Syed M et al. Apply LSTM-based encoders for network anomaly detection. These LSTM-based approaches show potential predictions. The survey concludes that the coordinated and uncoordinated checkpointing mechanisms face significant inefficiencies, and there is a need for tailored mechanism that minimizes checkpoints and optimize resource usage while efficiently recovering from transient faults. The main contributions of this research are, first one, the research introduces a novel checkpoint at intermediate node based communication-induced checkpointing fault tolerance mechanism for IoT environment that strategically place checkpoints only just before predicted faulty nodes by integrating LSTM deep learning algorithms. This minimizes useless and forced checkpoints, unlike traditional methods that place checkpoints indiscriminately across all or many nodes, and also addresses the deficiencies of existing FTMs. Second contribution is describing the transient fault occurrence scenarios and implementation of the fault detection algorithm. Our approach also uses LSTM deep learning for training purpose, using history of fault occurrences and new message logs and predicting new fault occurrences. Methodology goes as follows. The figure 2 is block diagram of the CIN CIC FTM using LSTM. Provides a visual representation of the proposed communication-induced checkpointing-based fault tolerance mechanism integrated with LSTM deep learning for transient fault detection in IoT environment. Step-by-step explanation includes, in the step 1, data collection and pre-processing will happen. Sensor in the IoT environment collect raw data which is pre-processed to handle missing values and ensure inconsistencies. In the second step, LSTM-based fault prediction will happen. The processed data is fed into the LSTM network to predict potential fault occurrences. The network is trained using historical fault data and uses its unique memory properties to predict future fault nodes. Third step is about checkpoint placement. Based on LSTM fault predictions, checkpoints are placed at nodes just before the predicted faulty nodes, allowing further targeted checkpointing. This minimizes useless checkpoints and optimizes resource uses. Finally, fault detection and recovery will happen. Upon fault detection, the system checks if there are valid checkpoints at the current or preceding nodes. It then initiates a rollback to the most recent checkpoint to recover from the fault, preventing the propagation of errors. This block diagram helps in understanding how the system integrates LSTM for efficient fault prediction, checkpoint placement, and recovery in IoT applications. The transient faults are sequence number fault, checksum error based fault, null character fault, and out of range fault. The CIC-FTM algorithm steps are very briefly explained here. In the first step, load historical data for fault prediction. Next, build and train LSTM model. Further, predict fault occurrences. Then run the main process to run the CIC-FTM, where it first places the checkpoints based on predictions, then save system state as checkpoint, then fault detection will happen, fault recovery using checkpoints, then build and train the LSTM model, then again predict faults, place checkpoints based on fault predictions, then recover from faults. This is an example for checkpoint at intermediate node based CIC-FTM. Consider this figure 4. As an example for understanding CIN, CIC-FTM. Firstly, CIN-based CIC induces checkpoints C1 and C2 at nodes N21 and N32, as these nodes are predicted to have faults based on LSTM algorithm. The sequence of message transmission is message M1 is sent from P4 to P3 and M2 is sent from P1 to P3, and likewise M3, M4, M5 and M6 goes on. If at M5 a fault is detected, CIC-FTM initiates the rollback propagation and will roll back to the latest placed checkpoint, that is C1, and restarts from C1. Again, Again, if fault is not recovered at M5, the system will roll back to the next latest placed checkpoint, that is C2, and restarts from there. Still, if fault is not recovered, then FTM returns to initial state and restarts the process from initial state. Still, if fault is not recovered, the FTM concludes it is hardware fault. We simulate the proposed model on the Google Colab platform using Python 3.7. Discrete event simulation spans 4 to 100 processes, generating messages via exponential distribution. Sensor frequency is set to 1 minute. This is adaptable based on adaptive application requirements. The sensor used in IoT agriculture include temperature sensor, humidity sensor, water level, light and moisture sensors. Training involves 7,000 plus data sets, 1,000 plus of testing for testing under diverse scenarios. Each scenario undergoes 1 to 15 tests, averaging parameters for assessment. Reconfiguring the sensor frequency to suit the needs of the application is possible. Hyperparameters are used to tune the LSTM-based prediction models. The most important hyperparameter combination that have direct impact on model performance are, as mentioned in this table 1. With the threshold value of 0.65, for which the prediction accuracy obtained is 98.5% as tabulated in table 2 and as shown in figure 5, which comes in the further slides. When the program is executed in Google Colab, and we have considered initially one sequence of execution where 10 processes are involved, and its network is shown here. That is as we get the output from the Google Colab. This is our first output what we have received for the network as shown in the previous slide. In this network, we have not received any we have not detected any fault until packet 5 is been sent, but at packet 6 we have identified, that means at process 6 we have identified a fault. These are the number of epochs. We have taken a screenshot of one epoch like this. We have tested for 1,000 epochs. Now, LSTM based fault prediction here, when fault prediction is done at node 4 and node 6, transmission of checkpoint is happening at node 4 and node 6. Checkpoint restored at initially checkpoint is restored at node 6. Now, when checkpoint is, for restarting is happening at node 6, then the data is transferred successfully. That means now the fault which was identified earlier at node 6, here at node 6, which is now recovered. Hence, we will get this message: the data is transferred successfully, and it will ask for the termination of the process, or it will continue with the new data. Now, the performance parameters for that sample, what we have evaluated is time taken to find faults is this many seconds. Time taken to transfer data from source to target is this many seconds. Time taken to handle checkpoint and restore is this many seconds. Turnaround time, that is our rollback time, is this. Number of checkpoints placed is this. Size of, the amount of memory consumed to place 2 checkpoints is 4 KB. Now, one such example or one such scenario was explained in the previous slides. Likewise, when we take 50 epochs, the average the accuracy, average accuracy, which is being calculated is this, the recall is calculated this, and F1 score is this. Like that for various epochs, these are the calculated, evaluated accuracy, recall, and F1 scores what we have got. And finally, we have taken average of those. This is the accuracy graph which we have obtained for 1000 epochs from LSTM based fault prediction accuracy. In this table 2, this also explains an average recall of 98.23%. This indicated that out of all the actual fault occurrences, the LSTM model successfully predicted 98.23% of them. And this high recall value indicates that the model is very effective at detecting most of the faults that occur, minimizing the risk of predicted faults, which leads to system failure. An F1 score of 98.1% indicates that the LSTM model has a well-balanced performance with both high recall and high precision. This indicates the model is reliable in predicting faults with minimal false alarms, which is critical for efficient fault management in IoT systems. Now, the proposed CI and CIC-FTM places the checkpoints at the identified faulty nodes. Figure 6 shows average number of checkpoints placed, average number of useless checkpoints, and memory consumption, CPU consumption for checkpoints in the network, and average back propagation time and fault recovery time when the network is of different node sizes like 4, 10, 40, and 100 nodes. The observations from the results obtained is listed over here. The CI and CIC-FTM using LSTM places checkpoints at predicted faulty nodes that are 15% of the total number of nodes in the network, hence significantly reduces the number of forced and useless checkpoints compared to existing models that often place checkpoints indiscriminately across multiple nodes. These checkpoints become useless only if fault recovery is successful by restarting from the most recently placed checkpoint, preventing the need to roll back to subsequent ones. As a result, the number of useless checkpoints is minimized, less than 10% of the total number of checkpoints. Existing checkpoint methods involve frequent, periodic, and indiscriminate checkpoint placements, leading to unnecessary memory consumption due to the storage of multiple and useless checkpoints. The CPU is loaded with the continuous monitoring and preprocessing of these checkpoints, reducing system efficiency. In contrast, the CI and CIC-FTM, since the checkpoints are placed at targeted nodes based on high accurately predicted nodes, minimizes the memory consumption by reducing the number of checkpoints stored and the CPU consumption, as the system is not required to constantly process and manage an excessive number of checkpoints. IoT networks face challenges with respect to its dynamic behavior and resource constraints. The reduction in memory and CPU consumption not only improves the overall efficiency of the system, but also ensures that the IoT application can continue to operate effectively even in resource-limited scenarios. Backpropagation time referred to the time required to roll back to the recently placed checkpoint from the fault-detected node. Fault recovery time refers to the time taken to recover from a fault by loading the previous consistent checkpoint and resuming execution from the checkpoint onwards. It includes the time required to transfer data from checkpoint storage to the program memory, reinitializing the execution state and continue its execution. The results indicate that the CI and CIC-FTM reduces the backpropagation time and fault recovery time by considerable margin compared to existing checkpointing techniques, which suffer from inefficiencies due to inconsistent node states and the domino effect. Because of predicted and targeted checkpointing approach, the overall number of checkpoints are reduced and are placed just before nodes predicted to be faulty. The back propagation time and fault recovery time are significantly reduced, in turn allowing for quicker system response even in presence of transient faults. So the conclusion goes like this: existing fault tolerance mechanism have inefficiencies due to checkpointing overheads. Existing FTMs place forced checkpoints either frequently, periodically, or indiscriminately that leads to useless checkpoints and unnecessary resource consumption and the domino effect. Proposed CIN-based CIC-FTM integrates LSTM deep learning model to predict fault occurrences that place checkpoints strategically, that is just before predicted faulty nodes. It is observed that LSTM makes 98.5% accurate prediction. Checkpoints placed are at less than 15% of total nodes in the network, and less than 10% of checkpoints become useless among them. This significantly reduces rollback time, fault recovery time, and in turn, overall checkpointing overheads. The CIN-CIC-FTM also offers reduced storage overheads and rollback restart recovery process, maintaining efficient operation in resource-constrained IoT environments, hence enhances system robustness against transient faults. The CIN-CIC-FTM is flexible for networks with more than 100 nodes and high-density IoT networks like smart cities, healthcare, and industrial automation. The proposed FTM can be used in adaptive and self-learning FTMs for dynamic IoT environments. These are some of the references which I have referred for my research purpose. Thank you.